Redefining farming practices. Innovations in agriculture to combat land degradation. Title: Redefining farming practices. Innovations in agriculture to combat land degradation. Introduction. 150 words. Land degradation poses a significant threat to global food security and the overall sustainability of our planet. Fortunately, innovative solutions are emerging to address these challenges and redefine farming practices. This article explores some of the most promising innovations in agriculture that aim to combat land degradation, restore soil health, and ensure a sustainable future for our agricultural systems. Agroforestry. Reviving biodiversity and soil health. 300 words. Agroforestry, a sustainable land management technique, combines the cultivation of trees and crops on the same land. By integrating trees into farming systems, agroforestry offers numerous benefits. Firstly, trees act as windbreaks, reducing soil erosion caused by strong winds, especially in vulnerable areas. Secondly, the tree roots anchor the soil, preventing both water and wind erosion. Additionally, agroforestry systems promote biodiversity by creating habitats for numerous species, fostering a balanced ecosystem that enhances natural pollination and pest control. Moreover, tree cover improves soil health by enriching it with organic matter, increasing water holding capacity, and promoting nutrient cycling. 2. Precision agriculture. Optimizing resource efficiency. 300 words. Precision agriculture leverages advanced technology to optimize the use of resources such as water, fertilizer, and chemical inputs. By employing techniques like remote sensing, satellite imagery, and sensor-based systems, farmers can precisely analyze the specific needs of their crops at different growth stages. This data-driven approach enables farmers to apply inputs only where they are required, minimizing waste and environmental harm. Moreover, precision agriculture aids in improving soil health by reducing soil compaction caused by excessive mechanization. The ability to analyze soil composition and moisture levels allows for precise irrigation, ensuring plants receive optimal water amounts, preventing waterlogging, and decreasing soil degradation. 3. Three key principles underpin conservation agriculture. Minimal soil disturbance, maintaining soil cover, and crop rotation. By minimizing tillage and adopting techniques like stripped tillage, no-till, or reduced tillage, soil erosion is significantly reduced, as the soil structure and organic matter content remain intact. Maintaining soil cover through practices such as mulching, cover cropping, and intercropping acts as a protective shield against soil erosion caused by rainfall and wind. Furthermore, crop rotation mitigates the risk of pest and disease buildup and enhances nutrient availability by alternating crop types. Hydroponics is a soilless cultivation technique that involves growing plants in nutrient-rich water solutions, using less water compared to traditional farming methods. Vertical farming utilizes vertical space efficiently by stacking crops in layers, using artificial lighting and controlled environmental conditions. These methods offer several benefits. They require less land, reduce water consumption, can be implemented year-round, and provide higher crop yields. Moreover, hydroponics and vertical farming minimize soil degradation risks and allow food production closer to urban centers, reducing transportation costs and carbon emissions. By avoiding synthetic chemicals such as pesticides and fertilizers, organic farming minimizes the risk of soil degradation and water pollution. Instead, organic farmers rely on organic waste and compost to enrich the soil with organic matter, improve its structure, and promote nutrient cycling. This not only enhances soil health, but also leads to increased microbial activity, which further supports plant growth. In addition, organic farming promotes biodiversity by providing habitats for beneficial insects, birds, and wildlife. These organisms contribute to natural pest control, reducing the need for chemical interventions. Crop rotation and intercropping are integral components of organic farming that help break pest and disease cycles, while also utilizing land more efficiently. This technique reduces water consumption significantly compared to traditional irrigation methods. By maintaining optimal soil moisture levels, drip irrigation prevents water stress in plants and enhances their growth and productivity. Moreover, drip irrigation helps conserve soil by preventing waterlogging and minimizing soil erosion caused by excessive surface runoff. The controlled application of water also reduces weed growth, as weeds are deprived of the excessive moisture they need to thrive. The combined effect of water conservation and soil preservation makes drip irrigation an essential innovation in combating land degradation. However, innovative soil remediation techniques offer hope for restoring contaminated soils. These techniques include phytoremediation, bioremediation, and electrokinetic soil remediation. Phytoremediation involves using plants to extract, stabilize, or degrade contaminants from the soil. Certain plants are known to have the ability to accumulate heavy metals or break down organic pollutants, thus detoxifying the soil. Bioremediation utilizes microorganisms, such as bacteria or fungi, to degrade or transform harmful substances in the soil into less toxic forms. Electrokinetic soil remediation involves applying an electric current to the soil to enhance the transport of contaminants towards collection electrodes, effectively removing them from the soil. These soil remediation techniques show great potential in restoring degraded land and ensuring its safe use for agriculture in the future. The IPM involves monitoring pest populations, implementing preventive measures, promoting natural enemies of pests, and using chemical pesticides as a last resort. By adopting IPM strategies, farmers can protect their crops from pests, while minimizing the risk of soil and water contamination. IPM practices focus on targeting pests specifically, reducing the impact on beneficial insects, soil organisms, and non-target species. This approach not only ensures sustainable pest control, but also contributes to the overall health of agricultural ecosystems. This holistic approach emphasizes the importance of biodiversity, soil health, and cosmic influences on the growth of crops. Biodynamic farmers utilize organic farming methods, while also incorporating elements such as lunar and celestial cycles, compost preparations, and creating self-sustaining ecosystems. Biodynamic agriculture focuses on building and maintaining a healthy soil ecosystem by using compost, cover crops, and crop rotation. The application of biodynamic compost preparations, which include specific herbs and minerals, enhances soil fertility and promotes the dynamic exchange of nutrients between the soil and plants. Additionally, biodynamic farmers consider the cosmic influences, such as lunar cycles and planetary alignments, when planning planting, cultivation, and harvesting activities. They believe that these cosmic influences can enhance plant growth and overall vitality. Moreover, biodynamic farmers encourage biodiversity by incorporating hedgerows, windbreaks, and creating wildlife habitats within their farms. Furthermore, biodynamic farming goes beyond organic certification by enhancing the spiritual aspects of farming. It emphasizes the farmer's connection to the land and the local ecosystem, encouraging them to develop a deep understanding and respect for the natural rhythms and processes. This approach fosters a sense of stewardship and mindfulness in agricultural practices, promoting a harmonious relationship with nature. Plants naturally absorb carbon dioxide through photosynthesis and release it back into the atmosphere through respiration. However, by adopting specific agricultural practices, we can enhance the process of carbon sequestration and promote long-term carbon storage in the soil. One such practice is the use of cover crops, which involves growing crops like legumes or grasses in between cash crops. Cover crops not only protect the soil from erosion, but also capture carbon dioxide from the atmosphere and convert it into organic matter through their root systems. The organic matter, known as biomass, decomposes over time and releases carbon into the soil, increasing its carbon sequestration potential. Additionally, cover crops improve soil structure, enhance water retention, and provide a habitat for beneficial organisms. Another technique for soil carbon sequestration is the adoption of no-till or reduced tillage practices. Traditional tilling methods significantly disturb the soil, releasing stored carbon into the atmosphere. In contrast, no-till or reduced tillage practices minimize soil disturbance, leaving crop residue on the soil surface. This residue acts as a protective cover, preventing erosion and promoting the accumulation of organic matter, thus increasing carbon sequestration. Furthermore, the application of organic amendments such as compost and manure can contribute to soil carbon sequestration. Organic amendments enrich the soil with nutrients and organic matter, improving its structure and moisture-holding capacity. As organic matter decomposes, it releases carbon into the soil, enhancing its carbon storage potential. Soil carbon sequestration offers multiple benefits beyond climate change mitigation. It improves soil fertility, water infiltration, and nutrient availability. It also reduces